Welcome to Module 8.3. In this module, we will extend the concept of DFT to two dimensions by defining a Fourier basis for the space of finite size images. We will see that although the mathematical extension is straightforward, the results are quite surprising with respect to what we're used to. In particular, we will see that the phase of the Fourier transform plays a much more crucial role in the case of images than it does in the case of 1D signals. Hi and welcome to Module 8.3, in which we will apply frequency analysis to digital images. We will first define the DFT for two-dimensional signals, and then we will look at the amount of information that we can extract from the magnitude and the phase of the DFT of an image. Fourier analysis of two-dimensional signals can be developed exactly as we did for the one-dimensional case. Since here we're concerned mostly with digital images, namely finite support two-dimensional images, we will only review the definition of the two-dimensional DFT. So let's consider a two-dimensional finite support signal of support big N1 times big N2. The DFT is defined as the double sum for the first index that goes from 0 to big N1 minus 1 and the second index that goes from 0 to big N2 minus 1 of the values of the two-dimensional signal over the support times the product of two complex exponentials whose frequencies are 2 pi over big N1, N1, K1, and 2 pi over big N2, N2, K2. The product of these two complex exponentials represents a basis function for the space of images of size N1 times N2. The DFT can be easily inverted, just like we did in the one-dimensional case. We take basically complex exponentials with the sign reversed, and we repeat the sum, taking now the DFT coefficients into the sum. Normalization is by convention applied to the inverse formula, and in this case we have to divide the sum by the product of big N1 times big N2. It is certainly instructive to look in more detail at the basis functions for the space of N1 times N2 images. These have the form that we have shown before in the DFT sum, and we can easily prove, like in the one-dimensional case, that they are orthogonal. There are N1 times N2 basis functions for an image of that size, and so it would be very hard to look at each one of them, even for images of moderate size. But we can try and plot some key representative basis functions to give you an idea of what the building blocks are for an image in Fourier space. We will show these basis functions by plotting the real part only as a grayscale image, where the value of 0 is indicated by black and the value of 1 is indicated by white. So here we have the space of 256 by 256 pixel images, and this is one of the simplest basis functions that we can plot. We keep the vertical frequency at 0, and the horizontal frequency spans one period between 0 and 255. So if we were to look at this in a three-dimensional space, we could plot, this is the image plane, and these are the values of the basis function, and this is a wave, a solid wave, that goes like this, right? So it goes down, and then it goes up again. And here we have the white part, and here we have the black part. We can invert the roles of the vertical and horizontal frequency, and we get an image which is simply a 90-degree rotation of the previous one. We can increase the horizontal frequency. At this point, for K1 equal to 2, we will have that the basis function spans two periods over the support of the image. This would be 3 periods. And if we swap the roles of the frequency, we obtain again an image rotated by 90 degrees. We can increase the frequency even more, and the density of these bands will increase correspondingly. Whenever the vertical frequency and the horizontal frequency are the same, the bands will be angled at 45 degrees. And by varying the frequencies, we can obtain a wide range of different angles for the bands. The good news is that the two-dimensional DFT basis functions are separable, and so the DFT can be computed in a separable way. In particular, we first compute a 1D DFT along the columns, So if this is our image of size big N1 times big N2, we first compute big N1 DFTs of size N2 along the columns, and once we're done with that, we compute 1D DFTs along the rows. So computationally speaking, we first need to compute big N1 DFTs of size N2. We know that we can use the FFT algorithm, so the cost will be N2 log in base 2 of N2. And then we need to compute N2 FFTs of size N1. So that would be N1 log in base 2 of N1, which is much less than N1, N2 squared, the cost of implementing the two-dimensional DFT directly from the equation. We can also express the 2D DFT in matrix form. For that, we need to express, first of all, the signal, the two-dimensional signal as a matrix. This is very straightforward because an N1 times N2 image is simply an N1 times N2 matrix. There is only the technicality that the orientation of the rows is inverted with respect to the Cartesian notation. So, for instance, in the Cartesian plane, N2 would go from, say, 0 upwards. But if we express, and this is our image, but if we express this in matrix notation, this element of the matrix normally is 0, 0. So there's a flipping of the vertical axis, but this is just a technicality. You will also recall the n times n DFT matrix that we saw in module 4.2. This is a standard DFT matrix of size n, where W, recall, is simply e to the minus j 2 pi over capital N. With this notation in place, let's look at the DFT formula once again. The inner summation is simply the product of the DFT matrix of size big N2 times the signal matrix. We call this intermediary matrix capital V, and capital V belongs to the space of N2 times N1 matrices. Then the outer sum can be expressed, the right product of the matrix V we just defined times the DFT matrix of size capital N1. And so the resultant signal is a matrix that collects the DFT values for the image. In compact form, we can express the two-dimensional DFT as the product of a DFT matrix of size N2 times the image times a DFT matrix of size N1. So now we know how to compute a two-dimensional DFT. Well, can we look at one? We could try and plot the magnitude of the DFT, since the DFT is a two-dimensional signal and therefore can be interpreted as an image. But this wouldn't work because the dynamic range of the DFT is way too big for either a monitor screen or a piece of paper to represent. We wouldn't have enough grayscale level to show the details. So we could try and normalize the values by dividing the DFT magnitude by its maximum value. And yet that wouldn't work either, because for images, on average, the distribution of the magnitude of the Fourier coefficients follows a curve like this one. So what we have here is a few outliers here that really go above the average values of the coefficients, and some tail outliers here that drive the value down. What we're interested in is this band between the extrema. So we take a two-step approach. First, we remove the flagrant outliers. For instance, the value of the DFT in 0, 0 is simply the sum of all pixel values. Now, for a grayscale images where all pixels are positive values between 0 and 1, say, this will be definitely a large value with respect to any other coefficient. And then to remove the tail, we use nonlinear mapping. For instance, we use a curve like x to the power of 1/3 after normalizing all values between 0 and 1. So for instance, if this is the range between 0 and 1, the nonlinearity will map this range like so, which means that the tail outliers that we've seen before will be squished in a band that is very close to 0, and so they will appear as black pixels. And the rest of the values, those that we're interested in, will occupy the bulk of the dynamic range of the medium. If we do that, we obtain something like this. So our little dog has been transformed in this cryptic image here, where if we look very closely, we can identify, for instance, some lines here and here that correspond to clear lines in the image captured by some of the basis functions that have these orientations. But by and large, it's very, very difficult to understand what's going on. We get a confirmation of our suspicion if we try to invert the Fourier transform starting from the magnitude only. So we take an image, we take the Fourier transform, we discard the phase information, and then we do an inverse Fourier transform from the magnitude. What we get, if we start with a dog picture, is this picture here, where we are absolutely unable to guess the original picture. What is more interesting is that if we do the same thing, but keeping just the phase, in other words, we throw away the magnitude, we set the magnitude uniformly at 1, but we keep the phase information, and then we do an inverse Fourier transform, we obtain the following image. So with images, the phase information carries most of the relevant information. So why is that? The idea is that most of the semantic information in an image is contained into its edges. Edges are points of discontinuity in the gray level signal. In 1D, you would represent an edge as a transition from, say, a white level to a dark level. This transition is what the eye perceives as an edge. Now, edges, therefore, are very localized in space, and they're not captured by the DFT's magnitude, which represents the distribution in frequency of the energy of the whole image. In order to obtain an edge from a combination of Fourier basis functions, on the other hand, their phase has to be aligned in a very precise manner. And that's why the phase information captures the intelligibility part of an image. A consequence of this is that the global DFT of an image is only of limited use in image processing.